Okay, assignment 13 is not an easy one, but it's a nice, combination of a lot of physics we've learned and some new physics that launches us into second semester when we talk about electric and magnetic fields. And I hope the first general video was good. This one is specifically on assignment 13, and I'm going to try and talk about problems 6, 7, 8, and 15. 8, 9, and 10 are the satellite problems. And so I'll try and address all those in this video. Let me start with number 7, the space station. And this is really should be familiar to us. It's a problem of circular motion. So when we have a space station, it rotates, and by adjusting the rotation, we can adjust the artificial gravity we're creating by rotating it. And if you think about a washing machine, if a washing machine rotates slowly, it doesn't dry the clothes very well because the force of the machine, the centripetal force of the machine on the clothes is small. But if it spins very fast, it creates a greater force. And so what we want this is to spin at a rate where the force it's exerting on us toward the center of the space station is equal to, where the centripetal acceleration is equal to the acceleration due to gravity, 9.8. If it goes too slow, then we're going to feel like we're floating, and if it goes too fast, we're going to feel like we're being crushed. So how do we approach that? Before we do that, I did download some images, so let me show you those. So depending on the size of the satellite, the inside part could look like a narrow tunnel. A smaller one, such as the one that's in the problem, or it could be quite a large, extensive. You can kind of see this curving up that way. So this is a very large one. And of course, the rotation rate will depend on the size. Here's another more modest size one, just more of like a small tunnel. That would be a smaller space station, similar to, and then here's just an artist's illustration of that kind of captures the toroidal donut shape of the space station. And so the amount of curvature is going to depend on how large it is. And if it's very large, the curvature it'll still be visible, but not that great. It'll be kind of flat in any local area. So this is all very interesting and futuristic thinking. So let's put these away, and let me pause the video and come back. It's a good idea to take a minute to try to understand the physics here. So we have this rotating space station. I've just simplified it. And there are people standing, right? We're in outer space, so this person's not going to fall. We're in outer space. They're just floating. But as they're moving around in this direction, their inertia is going to keep them moving in a straight line. And as the space station spins, it's going to push them back toward the center. So just like a washing machine doesn't really squeeze the clothes, it just pushes the clothes toward the center and they get squeezed. The water gets squeezed out. So each one of these persons is going to experience a normal force of the rotating platform pushing them toward the center. So let's look at the person in this position. And remember, we're in outer space, we're not on Earth. And so this person has a normal force of the space station pushing on them in this direction, and we want this force to be equal to their mass times the acceleration due to gravity. Now, if we look at a person standing on Earth, the Earth pulls down on them, mg, by gravity, And the floor that you're standing on pushes up on you by an equal and opposite force. So when we stand on Earth, this is the force we feel, the floor pushing up on us. And so this person's going to feel the same thing, the floor pushing up on them. And if these two forces are the same, the feeling will be identical. But it's important to realize in this case, the sum of the forces are not zero. Why? Because the person's accelerating. That's a centripetal acceleration. That's AC on your equation sheet. And it's either v squared over r or omega squared r. So write down this equation. Start with, so what relates force to motion is Newton's second law, right? So you're going to write down sum of the forces on this person equals their mass times their acceleration. The first time you do this, it's a little confusing. See if you can fill that equation out. Just try, pause the video and try, and then come back. Okay, notice what we're doing, what we always do. It's like, remember, this is your practice. We draw a free body diagram, and then we write down Newton's second law, and then we adjust it to the problem. So in this case, there's one force, the Fn, and it's equal to the mass of the person times their acceleration, which this is spinning at a constant rate, so that acceleration is a centripetal acceleration. Now for this case, we want Fn to be equal to mg, so it matches what we feel on Earth. So the Fn becomes mg, and the force, the centripetal acceleration force, could be v squared over r or omega squared r, right? From your equation sheet, you should know those. Since we're asked for omega, I'm going to use omega squared r. The mass cancels out. So anyone in the space station, independent of their mass, is going to feel a centripetal acceleration, which feels like the acceleration due to gravity on Earth. And so you simply do the algebra, and you get this. Make sure you go through this. Okay, now we have this, and we want to convert this to rotations per minute. So don't forget how to do units conversion. So take this and do the units conversion, and then come back and see how I did it. And if you didn't do it the way I do it, you're walking in risky territory. You need to do these methodically or you're going to make a mistake. So remember how we do units conversion. Take this and convert radians per second to rotations per minute. Okay, this is what you should have done. You write down the number. Then the first conversion factor is getting the radians to be rotations. So 1 rotation over 2 pi radians is the way you want to write it, so that the radians cancel and you're left with rotations, which is what we want. And then we want to change the seconds to minute. So the next factor is 60 seconds divided by 1 minute. Seconds over seconds cancel, and you're left with rotations per minute. That will give you the answer. So remember how to do units conversion. Sometimes you get lazy and you do it and you make mistakes. Okay, we're going to move on to problem 8. Okay, what I'm going to talk about now is a satellite going around the Earth. But this could be the moon going around the Earth. It could be the Earth going around the sun. It could be a moon going around the planet Jupiter. So this applies to a lot of things. And notice how similar this is to what we just did. Only in the case of the space station, it's the space station pushing the person toward the center. Here, it's the gravitational force on the satellite or the moon, holding it, constantly pulling it toward the center of the circle in a centripetal acceleration such that the orbit is stable. So we could take any one of these. Let's take this one now. That's our free body diagram, right? There's no other forces. Why? Because we're ignoring any effect of, say, the sun or other planets, which in this case we can do. So here we have a free body diagram. You're going to write down, like last time, you're going to write down the sum of the forces equals the mass times the acceleration. So try doing that. See if you can do that based on what we did in the last problem. Okay, I hope you were able to do this. Here's our free body diagram. Here's sum of the forces in the x direction equal max. What is the force? The force is Newton's universal law of gravitation. So G times the mass of both objects, the Earth and the satellite, times divided by the distance between their centers squared. So in this case, it's going to be the radius of the Earth plus this extra distance. In this particular problem, that's a fairly small distance because most satellites actually orbit very close to the surface of the Earth, not like this figure. Okay, so that's the force. It's equal to the object's mass. What object? The mass of the satellite, times its acceleration. It's moving at a constant speed, so that's omega squared r, or v squared over r. But in this problem, it asks for v, so I wrote v squared over r. Now notice, this is the radius of the circle it's moving in, which is the same as the distance between the planet and the satellite center. So this is the same r. So you can cancel one of those r's, and you can cancel the mass of the satellite, and you solve for v. And once you have v, I think you're good. And if you notice in the problem, it asks what happens if the satellite is 800 kilograms. Doesn't matter the mass of the satellite. It's independent of the mass of the satellite. It canceled out. So independent of mass, at a certain distance, an object has to move at a certain velocity or a certain omega in order for it to be in stable orbit. Okay, this is very important. It may come up on the quiz, it may come up on the final, and I know from past people are often confused about what to do. So just go through this until you're comfortable, you understand what you're supposed to do on any problem involving a celestial body orbiting another celestial body. This is the format for it. Okay, now I'm going to move back to question 6. The next two problems are energy. So let's remember our law of conservation of energy, LCE. And it says that work is the way we add or subtract energy, right? By friction, by doing positive work. But if there's no work done on a system, and the systems we're going to look at, like a satellite or a planet orbiting or rocket ship leaving, we're going to ignore air resistance and friction. And so the energy of a system that isn't added to or subtracted from will remain constant. That's the law of conservation of energy. And delta K is K final minus K initial, and K is 1/2 mv squared, final or initial. What we learned, or what you need to know if you haven't learned it, is that UG is no longer mgh. That's only on the surface of the Earth. UG now is calculated by G times the mass of one object times the mass of the other object divided by the distance between their centers. That will give you the gravitational potential energy. And if an object changes its distance from the center of the two objects, a distance change, the gravitational potential energy will change, and this is how you calculate it. Okay, now I'm going to pause the video just to draw another diagram. Okay, so here's the Earth, and here's the rocket ship, and we want to know how fast does it have to move to escape Earth's gravity. That's what we call the escape velocity, right? You know, if you throw a ball up, it'll go up and come back. And if you throw it faster, it'll go up higher and come back. And if you throw it a little faster, it'll keep getting higher and coming back. But at some point, what's the minimum velocity so that it actually won't come back and it'll escape the gravitational pull of the Earth, but we want to do that by energy. So how much kinetic energy do we need to get the potential energy at the surface of the Earth so that it's the way it works? This is a little confusing at first. Is the potential energy at infinity is going to be 0, right? Because if we take G m1 m2 and divide it by r equals infinity, we'll have 0. So in this larger way of doing gravitational potential energy, this is considered a negative energy. And so how much energy do we have to add in terms of kinetic energy? So what we have to do is the initial kinetic energy, think of it this way, the initial kinetic energy has to be what? So that it equals the initial gravitational potential energy, which is negative. The final gravitational potential energy at infinity is going to be 0. And the final kinetic energy can also be 0. In other words, if we start with a positive kinetic energy that equals the negative gravitational potential energy, then when this thing gets far away, it will have 0 energy. Okay, so see if you can write the equation to get that. Okay, I don't want to do everything for you, so here's 1/2 the mass of the rocket times the velocity you need to escape. So that's the velocity we're looking at, the escape velocity squared. That much energy has to account for the gravitational potential energy, the G, mass of the Earth, mass of the rocket, and the distance between them when it starts out, which is the radius of the Earth squared. Okay, solve that for V escape and see what you get. Hopefully you get this result. What's interesting about this, if you're an astronomer, astrophysicist, is that this would be the escape velocity for Earth. It's independent of mass, right? So whether it's a rocket ship or a tennis ball or a bullet or a molecule of air, if it has this velocity, it has the capability of escaping the Earth's gravitational binding force. But it works for any object, so it could be the mass of the sun divided by the radius of the sun. That would be the escape velocity, like particles boiling off the sun's surface. Do they go up and fall back, or do they escape? So the escape velocity of the sun can be found by simply changing this to the mass of the sun. We could do it for a neutron star. You could even do it for a black hole. And if you did it for a black hole, guess what you'd find the escape velocity is? It's greater than the speed of light. And that's why a black hole is a black hole, because nothing can escape, because nothing can go faster than the speed of light. So this is a very simple physics leading to a very, very powerful astrophysical result. All right, let's go on and do the last problem, number 15. Okay, go to 15, read the problem, read it through once or twice, and then draw a simplified diagram, a useful simplified diagram of the sun, the Earth, and the asteroid, and put in the relative distances, then come back. Practice doing diagrams. A good diagram is really very useful. So here's the sun. The Earth's going around the sun, 150 million kilometers away. And out in the asteroid belt, here's one of billions of asteroids going around at about 400 million kilometers. Now, how much is a million kilometers? Why don't you write that down? Come back. Okay, so mega is 10 to the 6th. Kilo is 10 to the 3rd, that's 10 to the 9th, and then we have 150, so it's 1.5 times 10 to the 11th. This is going to be 2.5 times 10 to the 11th. This would be 4 times 10 to the 11th. Okay, now this is a problem of combining. It's really a great problem. it combines energy and Newton's second law of force. All the physics we need to know, because when this asteroid collides with Earth, it potentially will release all its energy to the Earth. So if we want to calculate that, we have to think about its kinetic energy and its potential energy. And so there's three energies. It's going around the sun, so it has kinetic energy. And how do we find that? That goes back to what we did with the satellite problem, right? So the satellite problem equation will give us the velocity, just like we found the velocity of the satellite, we can find the velocity of the asteroid. That will be its kinetic energy, 1/2 mv squared. But when it falls to Earth, it's going to pick up that much gravitational potential energy. And there's actually a third energy that we don't do in this problem, but we should because it's large, is the gravitational potential energy that the asteroid picks up relative to changing its position to the sun as well. So there's an extra contribution that doesn't show up in this problem, but you should be aware of it because it turns out it's actually quite large. So what we want to do is first get the kinetic energy and then get the gravitational potential energy, because when this falls to Earth, it's going to gain that gravitational potential energy in the form of kinetic energy, and it's going to hit the Earth with that additional total kinetic energy, the sum of those two energies. Basically the law of conservation of energy. So the first step is to figure out what the velocity of this is, and then to figure out the potential energy. So do as much of that as you can, and then come back. Okay, here's what you need to do it. So first, you need to find the kinetic energy of the asteroid. So remember what we did, sum of the forces equals mass times acceleration. The force on the asteroid, remember it's not orbiting the Earth, so this diagram might confuse you. It's orbiting the sun, and so it's the sun that's doing the orbiting force. And so the G times the mass of the sun times the mass of the asteroid divided by that 400 million kilometers. But that's equal to the mass of the asteroid times its acceleration due to that force, v squared over r. And so just like we did last time, the mass of the asteroid cancels, one of these r's cancel, and we're left with this equation for the velocity. Once we have the velocity, now we can find out how much kinetic energy it has out here. But when it falls in, its total kinetic energy is going to go up, because it's going to have that initial kinetic energy plus the additional kinetic energy of the gravitational potential energy that it loses going from here to here. That's going to turn into kinetic energy. And so for that, you use this equation. And remember, so the final gravitational potential energy is going to end up being G times the mass of the Earth times the final position, right? When it gets to Earth, its distance from the Earth will be the radius of the Earth. It's not zero. Where does it start out? It starts out here, 250 million kilometers away. So that's our initial. So this number is going to be very small. You're going to see it's actually negligibly close to zero because it's so far away. But that kinetic energy, that potential energy change is going to be quite large as it gets close to the Earth. And that will be the amount of energy that you have to add to the initial kinetic energy. Just mentioning once again that there's also a contribution that it's changed relative to the sun, but we don't actually account for that in this problem. And so hopefully that will do it. I'm not going to work it through for you. I'm going to leave it there for you to finish.